In this video, we want to introduce the Purdue Model. If you've worked in OT security or read any standards documents, you've seen this referenced. It's the most widely used framework for organizing and discussing the structure of an industrial control network, and it's the vocabulary that the rest of this module uses. The Purdue Model doesn't tell you what equipment to buy or what vendor to use. It's a reference architecture, a shared language for describing the zones of an industrial network, what belongs in each zone, and how data should flow between them. Once you understand it, you'll recognize it in every OT security document, every network diagram, and every conversation with a security auditor. This Purdue Model divides an ICS network into numbered levels, each representing a zone with a specific devices and functions. The level numbers run from 0 at the bottom, the physical access, to level 5 at the top, the internet and external networks. Each level has a defined role, and the model specifies how data should flow between adjacent levels. The model was developed in the early 1990s at Purdue University as part of the reference model for computer integrated manufacturing. It was designed to help manufacturing companies think about how to connect their business systems to their production systems while maintaining appropriate separation. Today, it's cited in ISA IEC 62443, which is the primary international standard for OT security, and it's referenced as a baseline architecture across energy, water, and manufacturing and defense sectors. When a security standard says level 0 through 2 should be isolated from level 4, the Purdue Model is what gives those level numbers their meaning. Level 0 is the physical process itself. These are the things that touch the physical world. Sensors that measure temperature, pressure, flow, and level, actuators that open valves and start motors, variable frequency drives, and the other field instruments that make up the instrumented process. Level 0 devices communicate directly with Level 1, but they typically don't communicate over Ethernet. They use 420 milliamp signals, HART, field bus protocols like Profibus or Foundation Field Bus, or hardwired digital signals. From a network security standpoint, Level 0 is largely invisible to Ethernet-based tools because most of these signals are analog or field bus, not TCP/IP. The risk to Level 0 comes from attacks on the Level 1 devices that control them. Level 1 is basic control, the PLCs, RTUs, and DCS systems that read from Level 0 sensors and send commands back to Level 0 actuators. This is the layer where control logic executes. A PLC running a PID loop that manages a heat exchanger, an RTU pulling remote sensors along a pipeline, a DCS controller managing a batch reactor. All of these are examples of Level 1. Level 1 is a critical layer from a security standpoint. It's where an attack has physical consequences. A PLC that receives a malicious write command from an attacker doesn't know the command didn't come from a legitimate SCADA server. It executes the logic it was told to execute. Protecting Level 1 from unauthorized access, ensuring that only the specific SCADA servers and historian systems that legitimately need to communicate with PLCs can reach them, is the primary goal of OT network segmentation. Level 2 is area supervision, the SCADA servers, HMIs, and engineering workstations that monitor and control the Level 1 devices. SCADA servers pull PLCs for data, display process information to operators, and execute operator commands. HMIs provide local display and control at the process area level. Engineering workstations run the programming software that creates and modifies PLC programs, configures drives, and sets up instrumentation. These Level 2 systems are the interface between human operators and the Level 1 control systems. Level 2 is also where Stuxnet made its impact. It spread to engineering workstations running Siemens Step 7 programming software, modified PLC programs, and hid those modifications from the operator display. Level 2 compromise means an attacker can affect what operators see and what commands reach Level 1 devices. Level 3 is site operations. historians that aggregate and store process data, batch management systems that sequence multi-step production processes, report servers, and lab information management systems. Level 3 systems receive data from levels 1 and 2, but generally don't send commands to control equipment. Their role is data aggregation, record keeping, and reporting. Together, levels 2 and 3 form the operations zone, below the enterprise network and above the field control layer. The boundary between level 3 and level 4, enterprise IT, is where the DMZ sits, which is the focus of the next video. The Purdue Model levels matter because they define the basis for zone separation discussions. Devices in the same level generally communicate with each other and with the adjacent levels above and below them. Levels 0, 1 talk to each other, level 1 talks to level 2, level 2 and 3 communicate with each other. What should not happen, and what the architecture is designed to prevent, is direct communication between level 0, 1 and level 4, 5, or between the enterprise network and the field control layer with no intermediate control point. Every cross-level connection that doesn't follow this hierarchy is worth scrutinizing. A laptop from the enterprise network connected directly to a PLC at level 1 bypasses every zone boundary between them. A historian with interfaces on both level 3 and level 4 without going through a DMZ is a bridge that undermines the architecture. These are the architectural violations that attackers look for and will exploit. In the next video, we'll cover the DMZ and levels 4 and 5, the architecture that allows OT data to reach enterprise systems without creating a direct connection between the two worlds.